So good afternoon, morning, evening, whatever it is, wherever you are. It's my pleasure to welcome Professor Erin Brooks from the University of Idaho. Erin is internationally recognized researcher in agricultural water management, hydrology, and precision agriculture. And throughout his career, he has focused on understanding the interactions between water, soil, crops, and the environment, helping to develop more efficient and sustainable agriculture systems. His work combines field measurements, modeling approaches, remote sensing technologies to address practical challenges related to irrigation management, water quality, and agricultural sustainability. And today he will present how remote sensing can be used to identify temporary persistent cropping patterns and how this information can support both the implementation and evaluation of agricultural management practices. For you, SUSTAGRI students, I think this seminar offers an excellent opportunity to see how geospatial data and Earth observation technologies can be applied to understand and manage agricultural systems at both field and landscape scales. So please, Erin, the stage is yours.
Perfect. Thank you, Javier, and thank you for the invitation. And
You're welcome.
like I was saying, seems like a very great program that you've got going here, and pretty exciting to see where you guys will go with it. So, yeah, so let me share my screen here, and let's see if I can get this. Yeah, I see the screen.
Yes, very well.
Okay, good. Yeah. So, really is focus on a lot of my research is what I like it to do is science that's applied and useful. And so a lot of times I'm thinking from a end user perspective and remote sensing the patterns that you see from satellite imagery, even flying in a plane over landscape, it's just so much detail and interest and information there. And it's like, how do we get to use this? And so in different ways. And so I teach a precision ag class, and we know precision ag has been this promising technology, digital agriculture, and it's has a lot of promise to it. The question is it useful? Who is using it? How can we use the information that's out there? Anything from drone imagery to tractor mounted information to boom mounted to soil EC mapping. There's all sorts of information. We get spatial information. But is it really being used? We see even crop yield data down here from a crop yield monitor. How is it being used? We get these really cool patterns from imagery. And one of the first things you might think about using satellite imagery is make zones out of it. Okay, we got a high zone, a low zone. We can see from this topographic map that, yeah, these toe slopes are really greener than the hill slopes. That's great. And this is where I'm from in the Palouse region of Idaho. We have massive topography. So I get a lot of my research is looking at spatial variability and how do you manage spatial variability. And sometimes it's really obvious. We can see from a soil electroconductivity map here on the left that the toe slopes have certainly different soil types and the ridges and so for farmers that's information and sometimes like okay great now what do I do with this how do I manage this I know that rain dictates crop response. I know nitrogen does. I know soil carbon does everything. And so it's like how do we get this information in? And I don't know if you've seen this. This is one of the long-term surveys that Purdue University has done here in the United States. It's just surveys. These are dealers across the United States, and they just survey them and saying who is using different technologies and what are the offerings and what is the interest. And so you can see the percent of the dealers offering different services, and you can see the top one is grid and zone mapping. We see yield monitors, we see satellite imagery, drone imagery, soil EC mapping, robotic crop scouting, chlorophyll sensors. And it almost paints a really negative picture from like about 2020 to 2021. It's been a drop in this technology. It seems like more of these dealers like, I don't know how useful this is. It was really had a lot of promise for a while, remote sensing did, but now, gosh, we don't even offer it much. People aren't even seeing a use in it, which this came out when I did a similar presentation at Canvas, the soil science meetings last year, another presenter kind of brought this to my attention too. And so this is interesting. So are we not utilizing this data? Is this data just overwhelming and maybe it's not useful? If we look at um, the other part of the survey is looking at the profitability. What is profitable for a producer? What do they use? And they see that the number one is variable rate fertilizer applications. So putting this in a putting fertilizer in the low yielding, dropping it in the high zones, actually increasing fertilizer. So yeah, variable rate is good, but when you look at satellite imagery, boy, only 10% think that's even a useful technology. And so how do we, somehow some of this information is not getting used. And if you think of irrigation itself, and other irrigation surveys they do around the country, if the number of people actually using online or irrigation program, irrigation scheduling tools, there's very few that rely on that. They like to go out there in the field and feel the soil. And so why is the adoption of some of this technology not happening? And one of the things that has happened, and we know we've been collecting this data for a long time, Landsat goes back to the early 80s, and we have tons of data. There's so much information out there from Landsat imagery. Every 16 days of two satellites, every 8 days, we're having information on fields. We know Sentinel now is down to 10-meter resolution on some bands, and they're going back to 2017. So we have this historic library. And so remote sensing in the past has really been a snapshot. And let's just look at a snapshot and look at spatial patterns. But what we can do now is actually look at temporal variability and how do we take advantage of this historic library. And so I wanted to show you a few things that I've been working on and using. Of course, the other thing that's happened is these online tools, and I'm showing some examples from the US. I know there's some examples in other countries. If they're not there, they're going to be there fast. With AI, these tools are coming on board really fast. Here's what's called a climate engine tool, focused mainly on the United States, but these are online user-friendly tools for accessing this remote sense data. And what I've been working on is using on-farm trials. Growers in this regenerative ag movement, there's all sorts of things people are trying, and you may aware in your country that, growers here are using compost tea, biostimulants, bioamendments. They're doing a lot of really interesting things that are going on, and they want to know if it works or not. And they'll put their whole field in these practices, but they don't know, they don't have a control to determine whether it's working or not. And so I'm encouraging growers to set up on-farm trials. And here's an extreme one where we have a bare fallow field, but we were looking at cover cropping. And I said, well, put a strip in so we can see it from remote sensing, right? Sentinel imagery, it's 10 meters. So make it at least 30 meters wide so we can actually see it and we don't have mixed pixels. And we have a treatment where you have fallow, you have one cover crop mix, so we're going to terminate on a certain date, another cover crop mix. And so we have different trials you can do, and you can take advantage of remote sensing. And so actually trying to train growers to use imagery and use the response we can get as information. And in this case, this tool is really user friendly. In like 5 minutes, I can go in and get images from different dates. And here you can see the red is, the low NDVI. So that's the bare soil, and green is the high, the more vigorous crop. And you can see right in the middle here, that's where our field trial is. And you can see it, obviously. This is an average image from mid-June. And we can go in and we can look at July, and we can actually look at what it looks like in July. And we can even put points down. So you can actually do pixels or put points down, and then it goes back and it automatically extracts all the imagery going back in time. In this case, we're looking at cover crops and terminating cover crops at different times. And we can go back all the way back to here's 2019, 2020, 2021. We can see on those zones, were they consistent? I mean, one of the things you want to do with the field trials is make sure your soil variability, you don't have already some natural variability. Remote sensing allows you to go back and say, is this crop usually responding to the same point? Is this a good spot for a field trial? So I can see, in canola, we can actually see crop types here. Crop type, winter wheat, we have spring barley, we have spring wheat. And then in the cover crop year, here's the different responses where the blue line is representing the blue point, which was in the fallow. The green is a crop that was started to grow and got terminated about June. So you can see that the greenness index shows that didn't respond so well. Here's one that we let go into July, so the greenness is higher. And this is one going all the way to mid-July. And we can see just you can see a grower can see this, and you can see the difference already in the cover crop. The question, and here's a dry, we are in the Palouse, it's a more semi-arid, low precip zone, and we plant winter wheat instead of, and we plant the winter wheat after fallow. It's our cash crop. And so we don't want our cover crop to affect the yield on the winter wheat the next year. And we can see in this case, planting a cover crop, this blue line, the places when fallow had the greatest crop response afterwards. So we can see, oh, maybe it wasn't a very good idea this year to plant a cover crop. Having these trials and having this historic imagery, we can start seeing that, right? So this is just taking advantage of the long-term historic imagery to look at trends. And we can see in the same field with time or different points within a field what's going on. The ability to extract and look at this data is so powerful for growers, and it's maybe freely available is really interesting. The other thing that in the United States and here I couldn't see in Europe where they have a similar product, but I'm guessing there will be if not already is OpenET. And OpenET is one of the most powerful tools I think for hydrology and evapotranspiration and cropping that's come about. That's really changing the way we look at water resources management in the United States. And it's taking advantage of these satellite-based energy balance methods to actually get evapotranspiration. And one of them that was developed at the University of Idaho was Rick Allen with this metric model. I know in Europe it was Seaball. There's also different tools. There's 6 different tools to actually get remote sensing evapotranspiration. And this is just a map. It's now available across the whole United States. At first, it was just the Western United States. You can go in, you can explore the data. There's an API, you can call this information. And it's all using Landsat imagery in the historic library. You can go back in time and you can zoom in, either uses gridded output where you can actually go in and see distribution within a field using this Landsat imagery, or you can actually have field boundaries. And so they've extracted field boundaries. You know what the boundaries are. And on a specific year, you can go in and say, hey, what is the evapotranspiration seasonally? Within a month, and then for grid-based, you can actually get daily. And so what a powerful thing. Here we can see going back in time, we can see, oh, what has evapotranspiration done? You can go back and see what the crop types were, how has it responded? We know in this year was a heat stress or a drought year. We can actually start seeing this imagery, and so a grower can start seeing, okay, this is how this field has responded. Now, if you say at any given year, maybe we changed the practice or adopted a no-till or some other practice in a specific year, you can maybe start, all right, maybe I'll see a change here. But it might not still not be obvious, how weather is responding. And so what we found is an approach that we're using, and then here's getting to this idea of a persistent patterns. And so spatial variability is one thing with remote sensing. Temporal stability is another thing. If you can go into a grower and say, this is always this way, or statistically, we know this part of your field, or this field is always this way, or we are 95% confident. You can start talking about confidence. And this becomes more powerful for a decision maker. You can talk about risk. And so what we've done here is we've adopted a simple relative yield model, and relative yield for someone who has a crop yield monitor knows what this term is, but the distribution within the field. What's the relative yield distribution normalized by the field average crop yield? And I'll walk through this. So could we get relative yield, or relative NDVI, or relative evapotranspiration with the field, and we can look at how stable those patterns are, both within a field, which parts of the field are consistently poor every year, or comparing fields. Maybe it's the same crop in 2 different fields. Which fields in the watershed are consistently underperforming? Or which ones are overperforming? And maybe this has changed with time. So looking at temporal persistent is a really unique way and a powerful way that really hasn't been utilized much, both in practical management or even research so much. I think we underutilize this technique, and it's a very simple approach to do this. And so here's how it works. And I teach a precision ag class, and this is an example right out of a class. I said, okay, great. Should this grower consider adopting variable rate fertilizer application strategies? Which points would you recommend the grower vary for his or her fertilizer rates? And so the fertilizer rates, when we think of nitrogen, the greater the crop yield, the more nitrogen uptake the crop takes. And so likely the more nitrogen it requires. Well, if you have a low yielding point and the Palouse region here in the Idaho, we have really low yielding, eroded parts of the field. They're really low yielding, and in those parts we can actually drop fertilizer. And so if they have confidence the yield is going to be low or yield is going to be high, then they can change their management practices based on that. So imagine these are just 5 points in a field, and you have different crops in different years. We have spring wheat, SW, spring wheat in 2000, winter wheat in 2001, barley in 2002, spring wheat in 2003. They're different crops, so they have different yields because they have different crops. But we can look at the relative distribution by looking at the relative yield. And so here's how you think about it. And you can think if you had a crop yield monitor, you might have hundreds of these points, but you can average those points over the given field and say, well, the yield in 2000 was 62 bushel an acre, but we know in parts of the field we had 45 bushel an acre, in parts we had 80. Okay, winter wheat was higher yield, barley a little lower yield, and this is typical yields for this region. So then we can do is divide those specific yields by the field average. Like, okay, so now let's just divide it. And so now it normalizes. So now we can start comparing relative yields over time. And so now the relative yield, well, was 81% of the field average in point one. It's 118% in field two. Field 5.5 was 129. And we start seeing this distribution. Of course, if we average all these relative points over the field, we get 100% because that's mathematically what happens. So now we can actually look at these patterns. Now we've normalized them. We can actually start comparing those relative distribution. And what you can do is like, hey, I got 4 years, I got 4 points. I can get the average of those relative yields. So I got 0.1 on average is 95% of the field average. I can use the standard deviation of all those. Like, well, it's 11% standard deviation. And I can calculate a coefficient of variation. So now I start looking at temporal stability and start saying, okay, which one is consistently high or consistently low, and which ones are all over the board? Here, point two was really high this year in 2000, but it's really low in 2003. Wow, that's unstable. If I'm a farmer, I don't know whether I add a lot of fertilizer, not much fertilizer, because it varies. And so that part of the field, I may not have confidence. I may give it what the average is. But if you look at point four, it's always, every year, it's underperforming. It's on average 78%. I'm pretty darn confident at this point that I can drop my fertilizer rates. Point five, wow, I'm always overperforming. Maybe it has plenty of nitrogen there. Maybe I just keep it as is. Maybe I start doing something different. But this gives them, this is information that the decision maker can start making. So yeah, point five, higher yields, maybe increase fertilizer here, maybe explore that. Point four, lower yields, potentially cut fertilizer here. Points one, two, and three, maybe you don't do anything about it. So that's within a field, but you can actually replace these points by fields. What if I look at all the spring wheat fields within a given watershed or a region or the county or an irrigation district? We could do the same thing and just use field average, and we do a county or regional average and do the same thing. Instead of crop yield, boy, let's do NDVI. What if we take average NDVI over a season? Or let's look at evapotranspiration using from the metric approach or C-ball or whatever ET mapping approach. So, and then we can actually look at statistics like, oh, well, are we 95% confident? Is this, you can actually put confidence intervals, but have the statistics behind it. So I was just going to show you two examples of how we explored this, and one was in a dryland farming district, and one was in a irrigated example. And here in this dryland watershed, we have working with the Coeur d'Alene tribe who wants to bring salmon back to a watershed. They know there's some water quality sources of pollution. They know some of these fields have some issues. And the objective was, are there key land parcels in the watershed where we can actually target through management or even potentially buying land in order to reduce water quality loading and to a stream and potentially enhance the stream water quality to support salmon. So we came up with this logic. We said, we know that crop yield varies across the watershed. We know the relative crop productivity between fields is probably consistent. So if a yield's poor, then it's probably always poor. If it's good, it's probably always good. And we hypothesized that the unproductive fields, they probably have poor soils. That's why they're unproductive. And And then and we hypothesis if you're in unproductive fields, they probably have poor soils, they probably erode more, and they probably have more nutrient load or erosion load. So from a water quality perspective, not only do they not produce a good crop, they also are main sources of erosion. And then and typical in hydrology and water quality, 80% of load often comes from 20% of land. So we hypothesize that most of the nutrient load, sediment load is going to come from small parts of land. And obviously those parts of land are going to be unproductive. So they're less profitable to a farmer, and the farmer might say, I can't produce money off this anyway. Go ahead. I'm happy to sell this field, or I'm happy to receive some money incentive payments to try to improve that so I reduce water quality. So how do we go in and identify low productivity fields? Well, crop yield data, people are very private about their information on crop yield, but what if we could use OpenET and look at those that actually have more evapotranspiration? And then if we have fields that have the higher evapotranspiration, if we assume they have higher crop yield, then we can actually run another model, erosion model, and see those fields that have the highest transpiration and crop yield are those have the least amount of erosion. And then we can provide a priority list based on this. And so what we're using is a wet cloud model, it's an online model. Actually, a European version of this is available, it's an Australian version of this. And so it's a really cool online tool. It's another talk I could give someday, but if you wanted to check that out, go ahead. So then we need field boundaries in this because we're going to look at the average yield. So in this case, we used field boundaries from the USDA NAS app has a way to look at using remote sensing to actually get field boundaries. So you need field boundaries to actually get the average of a region. And so you can download this in the United States. You can use remote sensing kind of delineate things. This is a critical part of that in field boundaries. Then we took all the maps. This is OpenET evapotranspiration. This is a seasonal growing season evapotranspiration. We overlaid the fields, and then we did this relative ET analysis, and we can see the red, dark red are consistently low. The lighter red is significant, but not robust. So we have different criteria statistically. The dark green are always the highest, the best fields. And so we can actually start seeing, okay, so here's our poor fields, here's our good fields. And then we ran the model. It's like, okay, so these low fields that are consistently underperforming, are they truly having more erosion? And in this case, sure enough, those red areas are having higher mean sediment delivery. And so in this case, yeah, well, those are the fields that you may want to target in this case. And then we actually went in, well, can we take a deeper dive? Is there any characteristics of these soils that maybe cause them to underperform? And we can see there's poorly drained soils are often a condition, or there's perched water tables. And so we can actually look at some of those characteristics. So the summary in this case was low productive fields near the forest edge, oftentimes where they essentially logged a lot of these fields. They have the highest erosion rates. The frequently flooded fields, actually, where fields were put into wetland areas, they have poor productivity, but they still have low erosion. So even with poor productivity, they might be something you can still look at. So we were going through the process of soil sampling the low and high productive fields to look at these soil health parameters and go forward with that. So that was using a field example of this, and I'm going to show you now how we're doing it within looking at spatial variability within a field itself. So not comparing fields to one another, but comparing points within a field. And this is down in southern Idaho. The first was at northern Idaho, up where I am. And so this is primarily irrigated agriculture, corn silage, alfalfa, potatoes, sugar beet, wheat, barley. We all grow these. Oftentimes in this region, there's not crop yield monitors. So people here don't have crop yield mapping, so they can't do the relative yield. But evapotranspiration relates to crop yield pretty well. And so how about we use this? And so we have the metric model outputs across the entire region to look at seasonal evapotranspiration. And so we're going to look within a field. Are there consistent patterns that maybe there's ways that we can even do variable rate fertilizer within irrigated fields? And what are those persistent patterns? And it was a paper that was published a few years ago by my PhD student, Chimney Duvall, that you could read if you're interested in more how we did this. And so we did is look with those patterns. We're looking at individual points and compare it to the field average. and then start, hey, which ones have statistically significant differences? And you can see, in this case, the circles, they're center pivots we're irrigating. The middle part of the field has the highest, they're higher than average. The edges of the field, obviously, there's end guns. The blue areas are where there's low productivity. If you've been on a center pivot, you can see this. And oftentimes on the edges, it could be poor soils. It could be just the irrigation application rates are lower. We can even say, well, what's this, how statistically significant if a grower says, well, I need the yield to be at least 5% different. And then here's just saying, okay, we can do the statistics and say, well, it's at least 5% difference. So, maybe these poor parts of the field, maybe you have poor soils. Maybe you want to put compost or manure or kind of replenish these. There's different things you can do in response to this. So this is giving some real risk statistics to it. We did this, and you can actually download this Earth Engine app. We can actually look this over the entire region. It's really interesting, some of the patterns we're seeing, but you can see consistently on the edges of the fields, you can see lower productivity. The center part of the fields that tend to have higher water, higher productivity. And you can see this regionally across the whole thing. And what we did with this persistent patterns within the fields is actually using soil information, topography information, and we use this Baruta random forest analysis to actually see, okay, what are the factors that are driving this variability? And we can see the crop type, which crop you had. Some were more sensitive and some weren't. Elevation difference. Here again, soil parameters, total available soil, slope. And so you got seeing some even driving factors from a science perspective, understanding what's going on. And this is a field site we applied, and this actually looked at soil depth. In this case, you can see the shallower points, the smaller dots are actually the lower points, and they are actually driving a lot of the variability of evapotranspiration. So the soil depth was a driving factor in this field site. There's actually some really interesting edge effects that I won't get into so much, but you can see there's actually tended to be more consistent spatial variability within fields on the edge of a rangeland. And so advective effects kind of look like are going on here. Within the irrigation, right in the middle of the irrigation districts, we saw less pattern. So some interesting questions from some young scientist who wants to explore that. So in summary, yeah, we have these persistent cropping factors that can be evaluated. We don't even need a crop yield monitor to do this. These relative productivity maps and ranking could be really helpful from a water quality for directing practices. So the NRCS has programs to work with growers to identify, hey, how do we help you improve your soils? And if we have relative productivity maps, they identify, they can approach growers and say, hey, let's help adopt things. So this relative productivity is clearly linked to physical drivers. They make sense. And there's a lot of cool tools out there to actually explore this. So I encourage you guys to take advantage of the historic library. Look at these persistent patterns, generate tools, and start exploring. So I think with that, I will stop, and hopefully I didn't talk too fast and people could follow what I was doing, and I will open up to questions.